Okay.
We can hear you and we can see.
Okay, nice. So our work is an information-theoretic measure for enabling category exemptions with an application to filter bubbles. So I first want to give you some motivation. So personalized recommender systems, for example, the newsfeed system in Facebook, can entrap users in filter bubbles. So what is exactly filter bubble? So filter bubble is an intellectual isolation. So users are entrapped in the filter bubbles because they are only exposed to content that reinforces their beliefs rather than a diverse set of opinions. So as shown in the illustration here on the right, so the user inputs the personal data, his or her likes and dislikes to the system. The system will respond with even more targeted, personalized content to the user. So the user's original viewpoint will therefore be reinforced. So there has been a long-standing trade-off between utility and diversity. So if we want to go after utility, then we want the recommendation to be as accurate as possible, but may take the risk of entrapping users in filter bubbles. Or we can try to make contents diverse, but in the meantime, lose some utility metric, for example, the clicking rate. So these two goals apparently go against each other. So in our work, we try to answer, is there a way to remove this trade-off or strike a balance in between? So we propose the following interesting question. So how can we allow the user to choose which filter bubble to participate in and which ones to eliminate? So there are already several lines of related work. Some studies classic fairness measure, for example, equal opportunity statistical parity, and also some others introduce the concept of exemptions, where we have a resolving variable and the bias caused by the resolving variable can be exempted. Or there's another line of work study, the fairness in recommender systems. Some try to generalize the classic fairness definition into a collaborative filtering or rank-based recommender systems. Some other tried to study the collaboration or diversification behavior of the recommender system. There are also some other work that share a similar mathematical formulation with us, and there are many more. So what makes our work different is that we try to give users more control on the filter bubbles. So instead of just say we calibrate the result or we diversify the result, we try to strike a balance. We want to give user more control, let them make their own choices. And also, we also do exemption, but we only allow exemptions for certain category only, as we will see more details later. So what is our problem here? So suppose Alice is an expert in the climate change. So what does her article's recommendation should look like? So the color here means different conflicting viewpoints. In most cases, this could be the political stance of an article. So for climate change, where is her expertise? It is acceptable to only recommend the articles from one viewpoint to Alice, because Alice can use her expertise to make good judgments. But for all other categories where Alice is not an expert in, then we want the recommendation to be as diverse as possible. So as you can see the difference here for climate change, even if the recommendation is very biased or extremal, is still acceptable. So this is the problem we are proposing here. So if we want to formulate this a bit further, as you can see in the previous slide, we try to split the pool of article into two classes. The first class is what we call the exempt class, where it is okay to have biased recommendation. On the right is the non-exempt category, where we want the result to be as diverse as possible. So we use a variable CEX as the indicator here. Also, as shown before, the color code means the conflicting opinions. We wrap this into a belief-based attribute. We call it Z. Also, the size here means how likely Alice will like this piece of article. We call it prediction score of an article, denoted by Y hat. So what is our target here with this problem formulation? So for exempt category, the category where Alice is an expert in, we want the prediction score to not be independent of Z. We want it to fully reflect Alice's likes and dislikes, even though it is biased. So for non-exempt category, where CX equals to 0, we want the prediction score, the recommendation, to be independent of the belief-based attribute, because we don't want to entrap Alice in filter bubbles in the field where she is not familiar with. So given this intuition formulation, we can demonstrate our proposed measure here, which is called value-based conditional mutual information. It is very simple. So it is defined as the mutual information between the belief-based attribute, sometimes in most cases it could be the political stance, and the prediction score, given the fact that an article belongs to a non-exempt category. So we want to reduce this score. If VCMI equals to 0, then it is equivalent to say that the y-hat prediction score is independent of the belief-based attribute for all the articles that belong to the non-exempt category. So this is closely related to two other measures. First is mutual information, which does not really take into any exemptions into account. Another one is conditional mutual information, where we condition on all possible realization of the CX. If we expand this formula a bit, then as you can see, VCMI is actually also part of the CMI, but CMI also include another term at the end. This is the bias in the exempt category where we want to keep it. So if we use CMI for our previous stated problem, then when we are reducing CMI, we are not only reducing the bias in the non-exempt category, but also in the exempt category. So basically, neither MI or CMI can solve the same problem as our proposed measure VCMI. So I will hand control to my colleague Chenyu, and he will go through the experiment session for you. I think Chenyu can control the slide now.
Okay, thanks, Bowen. So in this experiment section, we will evaluate the effect of VCMI regulator in the model training. So we compare this VCMI regulator with the previously mentioned two other metrics, the mutual information MI and the conditional mutual information CMI. So we do this in a supervised training setting. So for each user, we will construct a classifier that outputs the likelihood of recommending each article. So we train this classifier using a labeled article recommendation dataset. So in our work, we experiment on two ways to integrate VCMI into training, SVCMI and DVCMI. So here in SVCMI, we use the entire data set to train the model and directly add VCMI as a regulator into the cost function. So on the other hand, in DVCMI, we train two separate models. We train two separate models for the exempt and non-exempt category articles. So we only use the VCMI regulator in the model for the non-exempt group. So the difference between these two lies in that in DVCMI, each of the two models is trained on partial data, but there is a clear separation of the exemption categories. So therefore, you would expect that DVCMI to have a better effect at preserving the bias in the exempt category, but it may have lower accuracy compared to SVCMI. So for the estimation of or computation of mutual information, we followed this method used by Dutta et al. So following their method, MI is approximated by calculating the Pearson's correlation. So this approximation is exact when the two variables here, here are Z and Y hat, are jointly Gaussian. So similarly, we can also use this method to calculate the value of CMI and VCMI. We first conducted an experiment on synthetic data. So in this synthetic data setting, we construct a data set by generating the article's features from composite simple random variables. So these features here used are a viewpoint intensity, which is generated from the political stance of this article Z, and article length, article freshness, and whether this article is in the exempt categories or not. Based on these features, we generate a user interest score by composite them together. And then we generate labels by applying a threshold function on the S. So here, therefore, this Y is affected by Z indirectly through the features we already constructed. We also use a simple MLP with 2 hidden layers as our classification model. So here is our experimental results. So here, the first column shows the CMI values conditioned on different values of exempt categories. So here is actually our VCMI proposed measure. So we would expect that VCMI will minimize the bias for this category, but preserve the bias for these exempt categories. Here, the x-axis shows the regularizers we used. So in this example, we can see that MI and CMI will minimize the bias in both groups, while our proposed VCMI regularizers only minimizes the bias in the non-exempt group, while it preserves the bias in the exempted group. So we also show that the bias using another metric called Jensen-Shannon distance between the likelihood of recommending each article conditioned on different values of Z. So we can see a similar result here. So we also report the AUC score of training those models. So the higher the AUC score is, the classifier is better at classifying the data. So we can see all regularizers decrease the AUC, showing fairness utility trade-off here. But the 2 VCMI models have higher AUC score than the MI and CMI regularized models, because the VCMI models only remove a part of the bias and preserves the others. So apart from this synthetic experiment setup, we also conducted a case study by evaluating VCMI on augmented real-world data set. So we get our original data, Twitter data from this Twitter news sharing user behavior dataset, which contains a set of users and their retweeted news articles. So since this original dataset do not provide enough needed information, we make some augmentations to it. First, we assign a political label to each news using a method mentioned in the original dataset paper. Then we generate the category label for each article using some NLP models. We, by assuming that retweeting means that user is interested in an article, we can construct a user item matrix. We fill in the blanks in this user item matrix by running a collaborative filtering algorithm. And the output of this collaborative filtering algorithm becomes our ground truth recommendation label. So after running these procedures, we have each article is associated with news category and article length, news publisher and publication time. We use these features as the input of our classifiers. So we also feed these features into a MLP model. Here, the measurement setting is the same as in the synthetic dataset case. The result, however, is a little bit different. So as you can see here, the VCMI, the S VCMI does not preserve the bias in the exempt category as well as the D VCMI does. So this is possible due to the limited expressibility of a single MLP model. So for the AUC, we observe no significant reduction of AUC scores for all models except for our D VCMI regularized models. So this is most likely due to the insufficient data needed to train 2 models in this VCMI. So as a summary, in this study, we argue that simply removing all bias in the news recommendation system is highly restrictive, and we should allow users to choose which content categories that should be exempted from this bias removal. We also propose VCMI as a metric for quantifying such category exempted bias. We also use 2 case studies to show the effect of applying VCMI. The case study include a synthetic data set and another real data-based data set. So we also noticed that there's a few limitations of our work. So first, we did not study the estimation of VCMI in our work. So it's possible that our current approximation is inaccurate in real-world settings. And secondly, in this study, we could not find any off-the-shelf dataset for us to evaluate on. So we turned to use our algorithmically augmented dataset. So we still need more accurate real-world data for further studies. So and third, we also noticed that our experiment settings are very simple. We used a supervised training setting. So I believe further study is needed to really apply VCMI to a practical recommendation system. Okay, thank you. And this concludes our presentation today. Any questions?